Hello everyone. Let us get started now. Previously we did some problems which were based on introductory probability and which might be important in the case of RL. And let me present first. Okay, so today we'll move away from the introduction and means like introduction probability that we had, and we'll focus on the RL part only. Uh, so, uh, so these are the problems that you're given here. So we'll first take off the first problem. Okay. Which is not a useful way to approach a standard multi-armed bandit problems with n arms. Assume bandits are stationary. So the bandit problem, you understand what happens is that it is inspired from the casino, where there is an arms giving you a reward basically. You can get a reward as you pull the arm, and but you have to pay for it anyway. Okay, the constant payment is there, but the reward can be or can may not be, maybe or may not be. Okay, so multiple arm situation, n arms. Okay, and so this is the classic multi-armed bandit problems. Uh, so as you could see from the lectures, that one approach is that so this is the first approach. Okay, how can I ensure that the best action is the one which is mostly selected as time tends to infinity? So we're choosing the best action, and in this problem there is a inherent stochasticity in the problem. Okay, that you don't know which arm will produce the reward all the time. Okay, some may produce, some may not, and sometimes it will produce more. Okay, so that is the idea. And you have to take samples from the bandits and ensure that as time tends to infinity, the arm which produces the uh, most reward, okay, maximum reward, okay, or you can say that is the best action, is selected. Okay, so that is one approach. Okay, and so that is we have learned from the lectures. Okay, and another, as you could see, that uh, that this is the optimal value. Okay, you have seen the chart in the lectures as well. Okay, and with the sampling we get towards the optimality as time tends to infinity. Okay, and this optimality gap is called the regret. Okay, So uh, so we are trying to make this area minimum as possible to have the minimal regret. Okay, because we will try to get to the optimality or maximum reward as quickly as possible. Okay, means which arm produces the maximum reward. Okay, so we'll get try to get to that as quickly as possible. Okay, so like that. Okay, so reducing the total regret. Okay, and as time tends to infinity, we have to minimize that. Okay, so that is a classical approach as well. Okay, so useful approach. Okay, so how can I ensure an arm which has an expected reward with a certain threshold of the optimal arm is chosen with probability above a certain threshold? So this is the pack optimality. You're taking an arm, okay, which has an expected reward um, within a threshold. I mean, like it is little less than the optimal one. But it is close to that. Okay, so we try to take those arms to have a to approach towards the optimality. Okay, so that is another approach that is has been explained in the lectures as well. So this is also correct. Okay, and how can I ensure that when given any two arms, I can select the arm with a higher expected return with a probability above a certain threshold? So we cannot means like if we choose two arms out of the n, okay, then we can miss out on the arm that is maximum, which produces the maximum reward. Okay, you may not choose that. Okay, and so they that way we can means lose that one. Okay, okay, so actually, so this is the actual answer. Okay, so just because it is not useful is called. Okay, uh, okay, so next let's move to the next problem, question number 2. So any doubt on this one? Any doubt?
Sir, can I explain the third point?
Third point. Okay. So it is the pack optimality actually. So the thing was that like we are choosing arms which has reward little less than the optimal arm. Optimal arm has the maximum reward. Okay, and so we keep doing that. Okay, and so so that way we reach to the optimal arm. Okay.
Okay, sir.
Hmm. Okay, so if you have any doubt, let's see, or maybe I can show the lectures itself. uh, so where was it? I think banded optimality. So you're able to see this one?
Okay, so what is the probably correct part here?
These are the three actually.
Either is the most optimal.
Huh?
Either is the most optimal arm. Or
Can you
No,
see?
no, no, no. It is
Yes, sir.
either approximately correct or not. Because we already only giving you approximately correct guarantees, right? So with a very high probability, it is approximately correct. right? With some small probability, it might give you an arm that is more than some distance away from the best arm.
Is it probably approximately correct?
Yeah, that's what PSC is. Probably approximately correct.
There's no probably.
Oh, that's okay. Probably correct would mean yeah, you're either optimal or not optimal. Yeah, probably approximately correct is, well, with some probability you are approximately correct. With some probability you are not. Right. So typically there are many ways in which people talk about this. That's one popular way of specifying this is called the epsilon delta pack, where epsilon refers to the approximately part, and the delta refers to the probably part. Right. So with the probability of 1 minus delta, okay, the solution I return to you will be within epsilon of the best arm. Right. So this essentially means probability that
the threshold is less than.
probability that q star of a, that's arm returned to you, is greater than that's one way of writing it, but that is not what the pack framework guarantees.
Sir, I have a doubt regarding option 4.
Okay. What is the doubt?
Sir, if there are only two arms and I know that one arm is optimal and the other arm is suboptimal, then why will I not always select the optimal arm? That will actually minimize my regret.
Okay. So the following is not useful.
Like if we had more than two arms, we would need some sort of exploration, but we have only two arms, so we can exploit, can't we?
But like we have given him n arms, okay, and so we are selecting two arms here, okay, out of the n, okay. So the thing is that I can select the arm with higher expected return with a probability above a certain threshold. Okay, so we are getting a higher expected return, okay. So okay, so the expected return is that probability of its occurrence is higher, okay, and okay, so a higher expected return with a probability so the thing is like this, okay. So understand, so out of n bandits, okay, you're given two here, okay, and so we explore it like this, that this had a higher expectation, so your expectation is e1 and e2, okay. Okay, so we are given that of the so the expected return is higher, okay. So what does it mean actually, that expected return that we see here? So this expectation that you're talking about is like you're getting some reward, say 1, okay. So in this problem, to simplify, what we do is that we take the reward as 1, okay, and in some cases 1, in other cases 0, okay. uh, okay, and we're getting it with some probability, okay. And we propagate this expectation to the top, okay. So that is the approach, okay. So suppose the expectation is 0.8 here, okay, and this is like 0.6, okay. So what has happened, like why is it not 0, okay. So sometimes we are getting 1, sometimes we are getting 0, okay. So like that, it has averaged out to 0.8 here, it has averaged out to 0.6, okay. So that is the expected return part, okay. And with the probability above a certain threshold, okay. So probability of its occurrence, now understand this one, okay. Like so some bandit, okay, might have a higher reward, okay, expected reward or expected return, okay. but it may not occur as many times uh, as the bandit which has lower reward. Okay, so what does it mean is that suppose the probability of occurrence, this is the expected reward here, and the probability of occurrence can be quite low because there are n armed bandits are there. Okay, so suppose I get a threshold, so the threshold they have told, I keep the threshold as 0.15. Okay, so then what will happen, the one with the higher reward may be rejected if it does not pass over the certain threshold. Okay, so you understand this one now?
Yes, sir.
This is the explanation. Okay, it may be eliminated due to the threshold.
Okay, sir.
Okay, and so the same type of argument is in the pack as well. Okay, so but it works. Okay, so let's see what that. Okay,
The applying this is called the epsilon probability guarantees, right? It is either approximately true very very close to. Does that make sense? Closely right. And setting. Both of these concepts, right? So, but there should be more. Okay. The third thing that I want to talk about is what is called pack optimality, right? Or not? It's not. I shouldn't really call it pack optimality, but it should be more pack complexity, right? So, here's a little tricky thing. So, pack stands for probably, approximately, correct. Okay.
I think you got it. Okay. Okay. Clear. Should we move to the next problem?
Yes, sir.
How do we move it? Shit. Okay. So what is the decay rate of the weightage given to the past rewards in the computation of the Q function in the stationary and non-stationary updates in the multi-armed bandit problem? So 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 the thing is that so there are stationary and non-stationary updates. Okay, just 1 minute, move to a better place. So there is stationary updates. My writing is really so there is stationary update and there is non-stationary update. So in the stationary updates, the rewards actually do not change. Okay, uh, okay. So so the reward that we get is fixed. Okay, so the stochasticity is not there in that case. Okay, and So the Q value is calculated using average of the past rewards, okay, giving equal weightage to all the rewards that we have got in the past, okay. uh, so what that leads to is that it is like a linear decay, okay. Means like actually I can very well relate to this one actually. The previous question we did during week 0. So here there was a question. That exponential decay. Just to wait a minute. No, this is the one. So question number 14 is the one, okay. So this is what is called, okay. So they are doing a weighted average when where newer samples are weighted higher than the older samples, okay. So so this is the non-stationary case we have, okay. So in the non-stationary case we need to have a relation like this, okay. So that high new samples are given higher weightage than the older ones, okay. But in the stationary case uh, uh, so we give equal weightage, okay. So the decay is linear, okay. I mean, get to that problem now here. uh, so uh, so the decay rate of the weightage, so what does it mean is that that in case of the stationary case, okay, um, so as equal weightage is given, okay, so the importance of the previous rewards is means it reduces linearly, okay. And but in the case of the non-stationary updates, what you're doing is that you're giving weightage to the more weightage to the newer rewards, okay, because the process has not come to steady state stationary. It is non-stationary situation, okay. So in that case what you're doing is that we are doing this one, okay. And as you could see, this was the answer, okay, here. So you're giving higher weightage to the newer samples, okay, and that leads to exponential decay in the older rewards, okay. So what you're going to get uh, is written inverted. I think this has to be the answer, but like uh, I think linear for the stationary case, right? Am I wrong? Am I getting anything wrong? Linear and hyperbolic. Is it a possibility? So anybody did this problem? Hello.
Hello.
Hello. Yes.
Yeah. Hi, Kapil this side.
Okay.
So, see, my interpretation of this was, I mean, going by the video which was uploaded for the lecture. So, I think in case of stationary, the factor which is attached to this is 1 by NA plus 1, right? And I think that NA, while it changes, so this that doesn't seem to be a linear factor as such. While in case of non-stationary, it becomes a alpha, which we keep it less than 1, but some constant. So, I mean, my interpretation was that it should be probably the former should be hyperbolic, and alpha, constant alpha in case of non-stationary leads to exponential decay in previous terms. So I chose the option 3.
Sure. So that is your point. Which lecture it was?
Um, so I think this was second last lecture probably.
This is the one, huh? Value based. Bandits one.
Yeah, probably. I think bandit or probably value function based only. I think, yeah, last lecture,
Uh,
just at the end of the video.
Expected value of R not changed, right? So you're assuming that the
Uh,
measurement is a coins, or what will happen if the head arm say 1,000 times, right? This number will become very small, right? It will be 1 by 1,000 plus 1, like it will be.
so this is the one, right?
yeah. So since na is also changing because it depends on number of times action A was taken in the past.
Okay.
So it's certainly not linear because I mean it's in the denominator. So and since it becomes very large, this decay is also quite sort of non-linear and probably can fall into hyperbolic.
So but you have to see that this QA are also average of the rewards at that point, right? So they have their own n terms as well. So you should relate with
Yeah,
this
but
question actually. Okay.
Mhm.
Actually, it's the same
Okay.
as this one. Okay. If you
Yeah, but this corresponds to the scenario where, like you rightly mentioned, it's the alpha constant for the non-stationary bit, right? So,
just see this one. Okay.
hmm.
That when we are so if you see here, okay. So let me write it down. Okay. So what do we get from here? Let us see that. Okay. So insert a slide here. Okay. And so the expression is this. Okay. So QTA is equals to QTA minus 1 and plus n1 by, so na plus 1 is the represents the which number the reward it is that we are getting from the bandit. Okay. And RT is the reward. Okay. And minus QT minus 1 A. Okay. So that we have got. Okay. So let us understand. Okay. That Q that we are starting with. Okay. Q1T. Okay. It is going to be R1 you can say. Okay. So after that what you're doing is using the expression you can see that if you written Q, so this one RTT. Okay. So Q2T. Okay. So we're going to use this average formula, and so this is going to be Q1, so R1. Okay. Plus this one is, this is 2. Okay. So it has to be 3, right? And this is R2 minus T minus 1, right? Okay. That is R1. Okay. So what is this Na plus 1 represents here?
Yeah, so this is the number of times action A has been taken in n attempts.
Okay.
So it's like an indicator function where whenever action A was taken, it is 1. So if I did it, let's say I toss the coin n times and I chose action A 5 times, so it would be 5.
So NA plus 1 is 5 in that case.
And A would be 5. I mean till T, the number of times I have chosen action A, and then plus 1.
Okay, okay. So this has to be 3, right here?
Yeah,
Okay.
should be.
So so what you get here is that 2R1, so it is 2R1 plus R2 by 3. So it will come continue like this, okay? And maybe we are doing some mistake. It has to be linearly added, I think. R1 plus R2, something like that. Okay, but so this is a stationary one, right? So in the stationary case, so this is a stationary case, right? Yes.
Yes, that is correct.
So in the stationary case, it has to be like a linear combination. Okay, means like linearly averaged. Okay. Uh, okay. Uh,
But isn't the interpretation of question is that if let's say Q1 was dependent on R1 as a factor of 1,
hmm.
and now Q2 is dependent on R2 as a factor of 1 by 3. So the
What you're
weightage of
saying? What you're saying? Repeat.
so Q1 was dependent on R1 by a factor of 1, right? So Q1 is equal to R1 we got,
Okay.
and now Q2 is dependent on R2 by a factor of 1 by 3.
Yes.
So the decline in that dependence is like 3 times in the first iteration.
Hmm.
So next iteration when we do, the decline in the dependence will be even,
Let
I
me
think
see
of.
the question. Okay. Uh,
So it certainly does not seem to be linear by that, going by that, right?
past rewards. Okay. So doing this.
So,
Okay.
so in case of non-stationary, it has to be exponential because it will be alpha, alpha square, alpha cube of that order, right?
Uh, in the case of the non-stationary, right? Yes.
Non-stationary.
Yes.
So that has to be exponential. I think that there the picture is much clear. So so in this case also, I think it should be non-linear, but yeah, whether it will be hyperbolic or some other form that is not sure.
Uh,
But in the given option, only exponential is
So
given to this option C.
yeah, so by elimination, it adds up to hyperbolic comma exponential.
but let's check. Okay. So let's see in the Google. So the question is the decay rate of the weightage given to the past rewards. Hyperbolic and linear. That is what it says. Okay, I guess we have to see this problem. Okay. Hyperbolic and linear. So Ram Prasad, what is your explanation? I guess we have to see this problem again, okay, and take it up in next week again. So moving on to the next problem. So the non-stationary case, so this is the thing, okay, and so in the non-stationary case, to give higher weightage to the recent reward, we have to take 0.1, right? Because uh, you can understand, like so this qt uh, up to that point, okay, this has to be plus 1. I think that little wrong there actually. This one is the correct one. Okay, now it is a n plus 1, makes sense now. So if you write it down again, so we start with this and then move to this is r1 plus r2 by 2, okay, and we go off like this. q3t by 3 dot 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 dot, and you get r1 plus r2 dot 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 rn by n. Okay, so what the point is, that in the stationary case, the decay rate of the weightage given to the past rewards in the computation of the, okay, so past rewards in this case is, first is like 1 by 2, and then 1 by 3, 1 by 4, falls like this. So what do you make of this? This is so we interpret it like this, right? And so what is this? I guess we have to see this problem again, and so this one is like, so is in the non-stationary case, okay, so if the alpha is 0.1, which actually is the same as this problem actually. I think we're having problem to interpret in the second problem, but in third problem it is the same situation as this one actually. You can see that so this is the average over till nth element, n minus 1th element, and we are given this extra means nth element xn, okay, to get the average up to nth element, okay. So to have higher weightage than the older samples, as I explained in the previous one, okay, you need to give a constant one, okay, constant alpha. So let me explain as well. So um, so you can just, so this is the average, right? So you can write it like this q t plus 1 a and so this is 0.1, right? Yes, 0.1 is the answer, okay. And the explanation I given, the explanation is same as this one actually, okay. And maybe I should open the previous slide only. Where is it? The writing doesn't come. Oh my god. To make a PDF, I think. Oh, so we'll change this one actually. Means like I think if I upload a PPT, then the writing doesn't come. I think to make a PDF and upload. And other than that, where I have uploaded is documents. So much. I think this is the one. God. Okay, so the idea is like this, okay, that so what you're doing is that so this one is RIT, okay, and so at every step what you're doing is you can write it like 1 minus alpha into q t a plus alpha times r t, okay. So so this you can see these are averaged over n plus 1, okay, averaged over n. So so these are averaged over n, okay. And now you're so so what happens is that with time, as n value increases, this will keep getting lower, but this one is getting a constant value weight to this reward 0.1, okay. So explanation is like this only. So this is the answer actually, okay, same as this problem I had explained previously. This one, if I could, this is one problem, like if I upload with the PPT, the only the my writing doesn't come there. So many documents. Problem. Acha, still in downloads. Have I not shown that one? Okay, looks like that. Yeah. So, but the explanation is like that only. That uh, that when you're giving a constant weight to the new reward, but uh, the the old rewards, the average of that is getting reduced with a factor of n. So 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 that is why you're means with time the importance of this or weightage of the old rewards will reduce, and this one will give when the new reward will be given the highest weightage. Okay, so this is like it. Okay, and so moving to the any doubt here?
Why have you not given alpha equals to n naught plus 1? So that will give more weightage to the new
So
returns.
so this one I can show easily. This is actually equal weight situation. This is what we are having here. Okay, so you can see r1, then this one becomes r1 plus r2 by 2. Okay, and it will move on to like this. So you're giving equal weight. Okay, 1 by 3 here, here 1 by n to every one of the rewards. Okay, understood?
So it will give n naught qt and then plus n naught plus 1.
But the, see what you're doing. You must remember that these q's are also average. Okay, so
Yeah.
the n factor is also inside them as well.
Yeah. So it's summation by n.
Hmm. Summation over r divided by n. Okay, and this is also like that. Okay, so this is okay, so summation over rt r r, let's not write t. So this is rk summation I k equals to 1 to t. Okay, divided by n. Okay, and this is 1 by n plus 1 rt is 2t minus 1, right? Something of that sort. Okay, and this is rt. So rt is a new one, should be more than rt minus 1, means the is rt minus 1 up to this point. So this is rt. Okay, or what should be that, like that. Okay, and this is so this is this one only. And so what you're saying seeing is that this will be n plus 1 times the sum. Okay, and divided by n plus 1 minus summation over that summation. Okay, so okay, you take the summation common. Okay, so this comes out to be, okay, so this comes out to be n times summation over n plus 1 plus rt. That is what we're getting. should have cancelled out the some indexing problem. Okay.
I think then if you take n naught plus 1, then it roughly becomes.
Overall, the thing is like this. This is progressing like this. From this you can see first R1 plus R1 R2 plus 2. Okay, like that. Okay. So if we see correctly what mistake we are doing here. So keep the indexes right. So we're t plus 1 we are calculating and adding rt here. Okay, and okay. So acha. So t plus 1 we are calculating and we are adding rt here. Okay, so this one has to be up to t minus 1, right? Oh, correct or not? Yes. And from k equals to 0 actually. Okay, and this is n plus 1 rt is there minus this sum. Okay, and what we get here is this qt what I've written here, qt is not there, so this sum will be taken common. Okay, and this will become by n, and this by n and n plus 1 as well, right? So what we're getting here is extra n, right? To n, and this 1 by n plus 1. Okay, so we take this one as the sum, getting n plus 1 here. Okay, let us write it down again. Okay, insert another slide here. So what the thing we are having here is that this summation k equals to 0 to t minus 1, and this is rk. Not able to write some. What happened? Some problem. Should do now. Gone black. Any idea how to correct this one? Not able to write. The draw option is gone. So maybe let's do it orally again. Acha has come back again. So this is r k. Okay, and what we're having is divided by n. Okay, and the same thing is here as well, so, and another one n plus 1 is also there. Okay, so when I take the LCM I'll get n plus 1 here. Okay, and minus 1, so n, right? N, so this would make it n by n into n plus 1 and in top we get the summation part, that is summation from 0 to t minus 1 k r rk, right? And the rest what we get here is alpha times rt1. So alpha was what? Alpha was this is plus alpha times this is 1 by n plus 1 r t, right? Okay, so this cancelled out. Okay, so you can see all the weights have equal weightage. Okay, now clear? Okay, proper derivation.
Yeah.
So this is the stationary case, okay, in which we get the all the rewards have equal weightage, okay, and the exponential one also I can do proper derivation. So there you'll see that with the higher means recent rewards have higher weightage. Okay, should I do that too?
No.
Okay. So from next time I will make a PDF of this and upload, so then we don't lose the writing. Okay, and okay, let's see if I need to solve more problems here. So assertion and reason. Okay, some of these you have to do yourself as well. Uh, I think the pack we have cleared it enough on that question already. Okay, can reduce this one. I think question number 8. And uh, so so now these problems, as you see, question number 9 and 10, I think, yes. So 9 and 10 I have this epsilon greedy and softmax exploration. Okay, so so these are in the lectures actually, so it should not be too hard. Okay, but let's see the 10th question. Okay, maybe I should take it in the slide only. uh, so so why softmax is better than the epsilon greedy approach? So softmax exploration makes the probability of picking an action proportional to its action value estimates. By doing so, it avoids wasting time exploring obviously bad actions. Uh, so so that is correct one, right? Okay, and we do not need to worry about decaying exploration slowly like we do in epsilon greedy case. Softmax exploration gives asymptotic correctness even for a sharp decrease in temperature. So the temperature part actually. So the temperature part you remember from this one previous day, that this is the temperature control. Okay. So so as you can see, in this problem what happened was that uh, that as the temperature falls, okay, so what happens is that this value shoots up. Okay, the probability shoots up. Okay, and compared to if it is less, okay, if it is more. Okay, so so even if there is sharp decrease in temperature, so the softmax values explodes. Okay, uh, so this gives a asymptotic correctness even for a this is not correct, right? This one, okay, and it helps us differentiate between actions with action value estimates q values that are very close to the action with maximum q value. Differentiate. Learn share about this one. So what answers you got this one? Option 1 is correct. Okay, and other than that, option 3, just to differentiate. What options did you get here? helps us differentiate. Option 3 should not be yes. I think only one I is the answer. Only one. So what you've got?
Why the second is not correct? We do not need to worry about decaying acceleration.
So as the sharp decrease in temperature, the softmax values are explode, right? And so in this problem, as you can see, that the video. This is the one. Softmax.
There is a small difference. Just remember that. Okay. Very, very hot, right? How sharp your probability needs to fall. Right? There are popular ways of selecting actions. In fact, epsilon greedy and softmax are also used in the full reinforcement learning problem. Smaller and smaller. So 19 action 2 0.0001 difference, right? Some small delta difference between the two actions. In epsilon greedy, what will happen? The one that is that 0.0001 higher will get the highest probability, okay, and the other one will have the same probability as all the other arms of being picked, right? But then in reality, I just want to be able.
It will give equal probabilities to all, and if you decrease.
Sir, if you raise the temperature, so what will happen is that the one that one with the if you raise the temperature, acha, yes, correct. Yeah, but here we are talking about decrease, okay.
And if you decrease it, then
So then the one having the maximum, okay, maximum softmax value will get most of the reward, and others will get less.
yeah. So resolution gives us asymptotic correctness even for a sharp decrease in temperature. Asymptotic correctness. No, don't need to worry about decaying.
So the
No,
asymptotic correctness here means that you're having a reward function means so you band it and suppose that is close to the maximum, okay, reward that will get in another bandit, okay, but so if sharp rise of temperature is there, okay, uh, okay, and a sharp decrease in temperature, so what will happen is that uh, the the one with the maximum reward will get all of the softmax probability, okay, and even little below that will not get mostly like anything. The sharp decrease means it's like close to zero, okay, that is what is considered here, temperature.
okay.
Okay, so so it does not give the asymptotic correctness, okay. The asymptotic correctness means that the one having a reward little less uh, should also get the close softmax probability, okay. In this case it will not get anything if the temperature is sharp decrease. So that's the point actually. Sharp decrease in temperature is actually the problem. But I think three is correct, right? Because it helps to differentiate, okay. But with a with a stable temperature, it's like not too low but not too high, okay. So then what will happen that some with a little lower value also will get some softmax probability, and you can differentiate between them. So it is 3, okay. And and the back one, which is following are two ways to define the value of selecting an arm or action. Better choice. So what you're doing here is that so this is the soft maximum, right? And this is just we are taking one means one this q and dividing by sum of all these. Okay. So so what do you think? What should be the answer? So so you can see that in the case of the that what do you call this softmax exploration means like we are using exponential to give a higher value to differentiate better among the two reward. Okay. And so this one is better because uh, it helps to differentiate that, but the option is not like that. Okay. Audition none of the above. Any catch here? None of the above. What does it mean? None of the above options. Which one? Yes. Next one. Okay, rest you should do. I think we'll finish here. Okay. I think we'll take up this question number 2 again in the next class. Okay. Okay, we finish here. Any problem? Any problem? No problem, right? Take up question number 2 in the next class.